2 plus ion exists. And one of our colleagues here, Wan T. Lee, won the Nobel Prize for making molecular beams in 1986, and he made exactly such molecules. Okay? And with this, we have the answer. Now, let's talk about p orbital linear combination. There are 3 p orbitals per atom, if you are in the p period, essentially. So you can have then a total of 6 atoms in the p orbitals per atom. Are you with me? Okay? There are 3 orientations of p orbitals. There is the x1 that looks straight at you. Okay? It lays down this way. Then there's the y1, which goes this way, from here to here, okay? So, and there's the z1, which goes this way, like I'm standing here. So I don't need to spear through here, and then I would have the px direction, okay? So now they can overlap constructively. All 3 of them can overlap constructively. But they're facing the other p orbitals differently. So 2 of them face them the same way, and 1 p orbital face differently of the individual atomic orbitals. And so if you look at those here, these are the y ones, these are the ones here, okay? So if you stand over there, they touch each other side by side. See, this one and this one would have to be in phase or out of phase. In phase, it would constructively interfere, and this would be out of phase, it would destructively interfere. So if they overlap here in the interatomic axis, this is the interaxis between the 2 atoms. That's the interatomic axis. This is not an interatomic axis, that's nothing, points away from them. This is the interatomic axis. If they interfere constructively, then they would have a bonding like this, okay? And this is a py would form a sigma bond. That's a sigma bond. So this is head to head, for example, and this would be an antibonding, actually, how it's written here, okay? That would be, if I had a plus here and a plus here, that would be constructive, okay? And so that forms a sigma bond, and now we have 2 more possibilities, no, actually 1 more possibility of forming bonds with the other 2 orientations. So if they go next to each other, like you stand next to me here, yeah, why don't you stand next to me? What's your name, please? Melissa? Okay. Melissa, we are going head to head and toe to toe. We're constructively interfering, okay? And we form a pi bonding and a pi antibonding molecule. If I would stand on my head now, which I'm not going to do, maybe you want to do that, but if I would stand on my head, I would be head to pose or head to feet, and feet to head. So we would be destructively interfering, okay? And we would form an antibonding molecular orbital. And so there's 2 possibilities. We can stand next to each other, or we could lay here on the floor, pointing at you. I'm not going to do that, okay? We lay here on the floor, then we would interact here, head to head, and toe to toe. Toe to toe, it depends how we lay. And so this would be, so these are pi molecular orbitals. And the interference is constructive here. Thank you very much, Melissa. When the constructive interference is here, in this direction, so that would be pi interference, and this would be pi interference. You have a pi bonding and a pi antibonding molecular orbitals, okay? So since you have one, you can have 2 electrons here and 2 electrons here, so this is 4 in this direction, and you have 2 here and 2 here, you could have 4 bonding there, so that would be a total of 2 pi bonds you could form, and 2 antibonding pi bonds, okay? So there's sigma and pi bonding. Now, there it is. Aha, here they are. So this is the interatomic axis, the py, and this is in your book the same way. So this would be the constructive interference. That's the bonding, see? Has a note here and has a note here. So this would be the sigma 2p bonding molecular orbital. So how many electrons can you put in maximum there? How many? 2. All the rules are still holding true. And now you have the molecular antibonding here. That's this head to toe, or toe to head. And so this would be the antibonding. How many electrons would you be able to fit in the antibonding? 2. Because, okay. Or would you be able to fit 4? No, you fit 4 in here in the bond, 2 in the bonding, and 2 in the antibonding. Okay? All right. And now this would be sigma. And now we're going to talk about the pi bonds. So the pi bonding would be look like this again. So this one would be above the plane and one below. Okay? This is a pi 2p, and that would be pi 2p antibonding. That's always the star. That's the antibonding. Of course, this has more nodes. You can see that this is going to be higher in energy. All right? So we have the p orbitals can form sigma and can form pi bonding. Okay? And the sigma is actually the more stable one, supposedly, most of the time. So there it is again. What kind of idea? It's written already. So if they constructively interfere, they form a sigma bonding pi molecular orbital. Okay? And if they destructively interfere, they form, and I haven't shown that to you, they form a sigma star anti-bonding molecular orbital. So this is this and that. And if you now the px and the pz, so you can have the px's here, they form a pi x bonding, and these are these 2 here, and these 2 here, the pz, for a pi z bonding, and the same thing is with the antibonding. You have a pi x and a pi z, so you can have 2, 4, 6, 8 in here. Okay, and here you can have only 2, 4 in there. That should be right, because that's the number of electrons should be jiving, as we say. Okay, all right. So let's play with this thing here. So you remember magnetism, para and diamagnetic? Boron, not moron, boron, okay? Boron has, now the s orbitals there, it's filled, there's nothing going on, okay? So you have bonding and antibonding, that's filled, okay? The 2s. So it's not interesting, nothing's going to happen there. The bonding happens with the p orbitals here, and so we have how many electrons in the p orbital? For boron, 1, okay? So we have 1 on each side, that forms the bonding molecular orbital, sigma bond, no. Actually forms the p bonding molecular orbital, that you need to know, you don't need to know that, but I will give you a scheme where you fill it in, that you don't get messed up, okay? It forms the bonding molecular orbital, and this would be the pi, because we talk about p, okay? P orbitals. And so that means, what's the bond order on this? You can read it, I know. 2 minus 0, 2 minus 0 is still 2, divided by 2 is 1. Okay, bond order 1, that's a single bond. Now we have the carbon. Carbon has, in each p orbit, in each has 2 p orbitals, so that's 4. All right, so you have to place 4 in bonding and antibonding, but you have the p, what was the p, what's this direction here? P, y, okay, py. So you have the px and the pz. So you put 2 in the px and 2 in pz, you don't need the antibonding. With this, the bond order is 4 minus 0, divided by 2, bond order is 2. Let's look at nitrogen. Nitrogen has how many in the p? 3, okay? So you have 6 electrons that you have to place. You put on each side 3, you put 1 of each side into the pi orbitals here, and then you put in the sigma orbitals. Now this is also sigma p, okay? So now there's no antibonding. Nitrogen has bond order. Okay, read it off, please. What's the bond order? Okay, 6 minus 0 is divided by 2 is 3. All righty, come on, wake up. All right, so would that be magnetic? So then oxygen, So oxygen has now 4. Okay, I have to place 4. I can only place 6 in the bonding, so I have to put 2 in the antibonding. Okay, bond order is, as you can say, 2, 4, 6 minus 2 is 4 divided by 2 is 2. Okay, remember the double bond in the oxygen we had in the Lewis structures? Fits. Okay, it would be bad if it wouldn't fit. Fluorine has how many? 5 p orbitals. Fluorine is, so that's 10, 2, 4, 6 in the bonding, and 2, 4 in the antibonding. That's a total of 10. Bond order is 6 minus 4. Is that right? 2, 4, 6 minus 4 is 2 divided by 2 is 1. So neon, would that exist, neon? 2. Bond order is 0. Okay, you have 4 p orbitals. How many p orbitals do you have? What's happening to my thing here? Okay, never mind. So you have not working. All right, you have how many? 1, 2, 3, 4, 5, 6. Okay, so a total of 12 orbitals. 2, 4, 6, 8, 10, 12. Okay, and with this bonding, 6 minus antibonding, 6 is 0 divided by 2 is 0. Okay, all right. Now, which one would be magnetic of those guys? Would be nitrogen? Would that be magnetic? Nitrogen would be not magnetic. How about neon? Doesn't exist at all. Fluorine, would that be magnetic? Yeah, it would be. Why you call it para or diamagnetic? Diamagnetic, exactly. It would be not magnetic. You say magnetic, but it's not magnetic. Makes no sense. Okay. Okay. Oxygen, would that be magnetic? Really? Well, let's do that then. Let's have a magnet. And let's first, if we can see that here, what Karen is doing, please. And let's switch that off here. Do we need the light, Karen? Yeah, we need the light, please. The lights, the lights. Okay, let me look at that oxygen first. You see that color? See that? You see color? What color is it? Say it loud, please. What color?
Blue.
What color?
Blue.
Blue. Okay. All right. Why is it blue? Why is it blue? Why do we have color? Because it does what? It doesn't reflect anything. What makes color? What makes your shirt or pink? It absorbs pink, obviously. A ray of wavelengths which are pink. So why is this blue? Because it absorbs everything but blue. Okay. All right. All right. So nitrogen. What's the color on this? Colorless. No light absorption. We come to this why this is blue. And actually, liquid oxygen is beautiful. You know that is. Oh. You feel better already? You know they have bars, oxygen bars. You can Las Vegas. Okay. All right. Good. Anyhow, so let's do that experiment. There we have a magnet here. If you can show that magnet, please. Yeah. And now we put some nitrogen in between. That's a very strong magnet. So if it's magnetic, it should get stuck between the magnet. Let's have a look at that. You see something? I don't. Okay. Yeah, it shouldn't be. It's not magnetic, isn't it? That's MO theory has shown us that it's not magnetic. Let's believe what we're doing here. Okay. So now let's do some oxygen. That should be magnetic. So it should stick it between these shoes, these pole shoes. Now look at the gas at the very end. Look at the gas at the very end. See that? Even the vapor is magnetic. Let's do this again because it's so much fun. Look at that. Isn't it beautiful? Is it ionic? No. It's not ionic. Okay. Look at the vapor. Thank you, Karen. Perfect. So now let me ask you this. We have nitrogen. Nitrogen is on here. And we do an ionization. So this is one ionization here. So we form N2+, plus, or we do an electron capture. And I want to know from you, which is true of the bond strengths of the products. If I use this here, and I do an electron capture, or I do an ionization, you compare the bond order of this here with the bond order of this and the bond order of that, and you tell me which is true of the bond order of the product of this and that. Is N2 larger than N2 minus, N2 plus larger than N2 minus? Are they about the same? Or N2 plus is smaller, the bond strength is smaller than N2 minus? Why don't you think about this and give me your answer, please? So all you have to do, you look at that graph here, you add an electron, you take an electron away, and then you determine the new bond order, and then you compare it to the one before. You don't need to have algebra or vector analysis, calculus maybe, okay? What is the answer? Was that done? Okay. Is she right? Yeah? Okay. Okay, we're done. No more clowning around here. Woo! Gotta get my blood circulating because it got all stuck in my feet. Okay, now, nitrogen has bond order 2, 4, 6, minus 0 is 3. Is that right? It's a triple bond, remember? Triple bond. So now you add 1. You add 1, what would that be? Then you have 2, 4, 6, minus divided by 2 is the bond order. So you compare that bond order with the next one. Or that would be adding would be this here. What is it called? Electron capture, okay. And, or you would take an electron away. So you take one away here, and then you determine the new bond order. Now you compare it with each other, and you give me please the right answer, okay? Discuss it with each other. Come on, discuss it with each other. You gotta have to sound bad. Good, draw the diagram, exactly. That's what you're gonna do in the final. No, in the midterm. But I actually give you a scheme where you have to fill in the electrons. What is it? What are you getting? Mm-hmm. If you know why, that's even better. Yeah. What are you getting? What are you getting? You know, guessing doesn't count. You need to get the answer right. Yeah? Okay. If you think that might be the right answer. Okay. Let's have a look if my heart gets better. Yes. Okay. At least you listen. not doing anything. Okay, it's going to be B. Now let's have a look at this. And on nitrogen, we had bond order was, what was the bond order? 3, okay. Okay, now we have this one. What's the bond order of this one? But let's see, there's something missing here. 2.5, yeah, okay. This is bonding and this is antibonding. Is that right here? Yeah, okay. 2.5, this is 6 minus 1 is 5, divided by 2 is 2.5. And this one, you have one less. This is 5 minus 0 is 5, divided by 2 is 2.5. And so what was the question again? The question was, the question about which is true of the bond strengths of the products. So this one and this one is about the same, so it was B then the answer. Okay, because it's so much fun, I want to see how well you listen to me. Which process involving a photon is responsible for the conversion of an oxygen triplet to a singlet? Triplet is paramagnetic, singlet is diamagnetic, okay? That's a singlet, okay? All right, so is it A, absorption, B, emission, or C, ionization? Why don't you think about this? Let's see if you listened to me 5 minutes earlier. So what's the structure of oxygen? Oxygen is this here, okay? And so what does it do? And it takes up energy. What could it do? How would it take up energy? We are not finished yet. We still be at the last minute, and I want to give you another hint because we're going to continue with this on Monday, and there will be a test. No. There will be no test, okay? Okay. All right, there will be no test. Okay, we still have, I need a second counter. So what is the process? What color is that oxygen? Blue. So what's the process? Absorption, okay. Now everybody has it right. Everybody give me the right answer. Of course, absorbs. It flips one electron, and this is a high energy state. And what it does actually flips it, and it comes back. Flips it, relaxes, and this is why this is blue. Okay? So let's see what the answer is. Oh, what a success! Okay. See you on Monday. I will show you the solution in more detail on Monday.